Great. So let's take a quick look back at the first two decision reports, which hopefully your teams have been able to submit a copy of those already. Let's take a look at what they've done for us so far and how we're going to be able to take our next step forward in the marketing project. So in the first two decision reports, your team's main job was to take the set of data that you were given and figure out how to, first of all, understand what that data was telling you, and then secondly, to extrapolate from that data to be able to make some simple predictions about what that data told you about the demand for the product that you're marketing in the national market that you were assigned. So the marketing data that you were given showed you, first of all, how large the potential national market for your product was. And then secondly, the results of test marketing that product in each of a handful of different test markets. So in the data that I'm using as a demonstration, there were 5 test markets, so 5 different price points at which you were testing your product in those markets. And each of those test markets is considerably smaller than the national market itself. So the first task in Decision Report 1 was to scale up the size of the sales in each of your test markets to predict what would be the sales in the national market for each of those price points. So you did some proportional reasoning to scale those up to figure out what are the actual quantities in the national market that would sell at the various price points that you were charging. And then you took that data that relates quantity to price, quantity on the x-axis, price on the y-axis, and created a scatter plot out of that, which depicts at least 5 points on what we might think of as our demand function. The demand function is the function which relates quantity to price, thinking of quantity as the independent variable, price as the dependent variable. And we use technology, so we used both Excel in class, and we also showed how to do it using Desmos, which I'm going to switch to in a second, to perform a quadratic regression. In other words, find a second-degree polynomial function which best matches the data points that are part of our data set. So in Excel, you can run a regression. It gives you an equation that looks like this. In Desmos, launch that here from our live textbook. In Desmos, same deal. We can get an equation that best matches, best models this data, get the regression coefficients out of this analysis right there. So the first decision report was just to do that and then to figure out whether or not the market, the national market for your product, given the data that you have in the project, whether that national market supports a sales quantity of 1.5 million units. And since the quantity in our project is being measured in thousands of units, selling 1.5 million means finding a place where the quantity is equal to 1,500. So that was really the question in decision report number 1, was, is it possible, given your data, for the quantity to equal 1,500 at a price that actually makes some sense business-wise? We can look at it from a couple ways. We can look at it graphically. So just based on my graph right here, if I try to go all the way out to 1,500 on the quantity axis, I find out that I can't quite get there with a price which is positive, right? Similarly, if I plugged in 1,500 for Q into my demand function, it would spit out a price for me which was a negative price. In other words, if I, in my model here, wanted to get rid of 1.5 million units, I would have to pay people in order to take them, in order to take that many. So that's not going to be a possibility. So that was the first of the decision reports, was just to take that quadratic model and do a simple thing with it. Just figure out whether Q equals 1,500 is a possibility. In my data, that answer is no. Decision report number 2, we had to get a little bit more specific about the limitations of the model. Specifically, we want to know whether or not, what is the maximum quantity that we could get rid of, and what's the maximum price that we could charge for our product in the market. And it turned out that those 2 questions were answered by the intercepts of the demand function. So on the one hand, the vertical intercept, so that would be the point which is up here. The vertical intercept of our demand function gives us a sense of what would the price be if the quantity were equal to 0. Now, why would the quantity be equal to 0? It would be equal to 0 because we're trying to charge so much money for our product that we have no customers left, that nobody would be willing to buy our product in excess of that quantity. And so we can find that just by plugging Q equals 0 into our demand model. In my data, at least, that's $558 per unit. If I try to charge that much or more for my product, I've completely priced myself out of the market. Meanwhile, the horizontal intercept the x-intercept if you like, tells us what's the result for when the price is equal to 0. And the price would be equal to 0 if I'm trying to give away as much of my product as possible. So here that's Q equals 1182, which is about 1.2 million units of my product. That's the most that I would be able to give away if I were to just give it away for free. So I can tell my production staff, we don't need to have capacity to produce any more than this much quantity, because even if we did produce more than that amount of quantity, we wouldn't be able to get rid of all of it. So those two intercepts, which we can get using the formula and also looking at the graph, tell us something meaningful, as intercepts almost always do in one of these models. So that was the first 2 decision reports. And where we need to go next is we need to figure out how to get some more nuanced information about not just our demand function, which is what we started the project with, but also the functions that we ultimately care about most in the project, which are the revenue function, the cost function, and finally the bottom line, the profit function.